Nice work. Back in action. Hello?
We're still giving out midterms today, right?
Yes, I am.
Woo!
Oh, let me just, if you just stay there, okay, I'm gonna just use hand sanitizer.
That's okay. No rush.
Make sure. Yeah. Okay. Your name?
Wakeford, Sydney.
Okay. Here you are. I'll just set it up here and you can just grab it.
Perfect.
Okay. Step back.
Thank you.
Okay. There you go. Let's see here. Okay, that's good. Sorry, did you get your midterm back?
Yes, sir.
Okay, good. Glad you're back in operation. It's even better now because it's not so flaky. So hopefully this will last for the rest of the semester.
Yeah, hopefully no more night classes.
No more night classes.
Although I like the change of scenery.
Oh, yes.
That was fun.
So I'll probably broadcast from my house when we go online after Thanksgiving.
Oh, yeah.
Most likely.
Yeah, I keep forgetting we're doing that.
You'll get to see my dog.
Yes.
The dog may make an appearance. I actually have a welcome video that was just a test video. I haven't posted it, but it actually has my dog in it. Sure, no problem. Please. Sure.
Thank you.
Okay. Good. Okay. Ooh, looks like we might be a little hot today. Let me kick the volume down. Okay, can we do a sound check? Can someone on Zoom say something?
Oh, you're good.
Hello.
Maybe a little louder.
Hello.
Try one more time.
Hello.
Maybe I do have to jack it up. Okay, one more time.
Hello. Hello. Hello.
Oh, it sounds kind of low. Okay, let me keep on going. Okay, go ahead.
Hello. 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 Hello.
Yeah, that's better. Okay, yeah. Okay, let's begin. So I apologize for the technical difficulties on Monday. It turns out that when I talked to the computer staff person, he said that perhaps a software update on the machine in the classroom actually kicked me out, because in order for the iPad to connect correctly, I need the correct permissions. So yesterday I came in and worked with computer person, and we got the iPad to work correctly because he had to use his admin to actually get the iPad to connect. So you just can't connect to it automatically. You need administrative privileges. So hopefully this will work for the rest of the semester. I do appreciate people coming to the night class on Monday. So if you weren't able to make it, I did post the video online. Okay, and what I'll do today is I'll actually review the video. I'll review parts from the video that we covered involving the basics of determinants. Okay. So the next thing I want to talk about is the upcoming schedule. So I believe homework 6, which is this homework. Let me see if I can I write? Oh yeah, sure. Okay, so I can now write. Okay, so this homework is actually due today, right? And as usual, just submit on OneNote. And then the next homework, 2.9 and 3.1 is due next Wednesday. And then we kind of scroll up here. And then 3.2 and 3.3 is due the following Wednesday, okay? And then this one over here, so this homework is due after the midterm. So this is due in week 12. Okay, so that's just like what we did with the first midterm. I don't like to have homework actually due on the midterm week. All right. Now, what we'll do is, let's see, so the midterm is through section 3.3. So probably by the middle of next week, I will have covered all the material for the midterm. Okay, so 5.1 and 5.2 won't be covered on the midterm. So everything before this is for midterm 2. Okay, and it will be inclusive too, okay, because the final is also comprehensive. Okay. All right, and the midterm will have basically the same format, 5 problems, 20 points each. You know, it's going to be based on the homework type problems. And then I hope to review. So what I'm going to do is I'm going to push the material up a little bit because week 10 is a short week because of fall break. Okay. So I'm going to move the material from 5.1 and 5.2 back a little bit, so it gives us a little bit more time to review. So I haven't set the midterm dates yet, but most likely they'll be in week 11 on Wednesday and Friday again. Okay, but they're not quite set yet. I just want to make sure that this schedule that we're working out is feasible, and I think it will be. I'll know by next week, and we'll set the midterm dates by next week. Okay, any questions on this? No? Okay, good. All right, so we'll escape out of here. We'll go to the notes, and we're ready to fly. Okay, so today what we'll do is we'll first review determinants. So let me do that for you. So we are on the topic of determinants. Okay. All right, so the goal is the following. So A is an n by n matrix. And so what we want to do is we're going to define a numerical value for A called the determinant. So we're going to define the determinant of A. Okay, this is a numerical value. Okay. And then the next thing we're going to show is that A is invertible. And we'll show this later. We know what it means to be invertible. And we want it to happen if and only if the determinant of A is not equal to 0. Okay, so we want this number, if it's 0, the matrix is not invertible. If it's equal to 0, sorry, if it's not equal to 0, it's invertible. And if it's equal to 0, the matrix is not invertible. Okay, so we've seen this before in the 2 by 2 case. So we have the matrix A, and it's just a typical 2 by 2 matrix, A, B, C, and D. And then for this 2 by 2 matrix, we have a formula for the inverse. So A inverse is equal to 1 over AD minus BC. And remember what we have to do. We have to switch the A and the D and negate the B and the C. You can remember it that way. Switch the A and the D, negate the B and the C, and then divide by AD minus BC. Okay, and so the inverse is going to exist as long as the AD minus BC is not equal to 0. And that's going to be, in this case, the determinant. Okay. All right. So on Monday, we actually defined the determinant in general. Okay. So the general definition of the determinant is as follows. So what we did first was we expanded along the first row. So we had these things called minors. Let me see, let me define minors first. So if I define, okay, let's do it this way. So A is going to be a matrix, and it's going to have entries like A11, A1n, and AN1, ANN. And then what we want to do is we want to make a submatrix which is smaller by one dimension. So if I have an entry Aij here, the idea was I want to cross out the ith row and the jth column. Okay, and then I form Aij, little Aij. Okay, so let Aij be the n-1 by n-1 matrix obtained by deleting the ith row and jth column of A. Okay, and I don't know, we want to do a quick example here. So here's an example. So let's say the matrix looks like this. 4, 3, 0. So this is an example from last time. 6, 5, 2, and 9, 7, 3. Okay. So let's compute A23. Okay, so where's the 2, 3 entry? It's in the second row and in the third column. It's this entry over here, right? So what is A23 gonna be? Anyone? What matrix?
Four zero nine three.
Let's
Or
see.
no. 4397.
Good. 4, 3, 9, 7. Very good. So we're going to cross this one out and cross that out. Okay, and that's what you do. So you start with the 3 by 3, and then you get a 2 by 2 matrix. Okay. All right. So now I want to define a cofactor. So Cij is going to be equal to -1 to the I plus j, and then I'll only take the determinant of Aij. Okay, so this is the definition of a cofactor. Okay. Now, in the cofactor, remember the sign is actually put into it. So when you calculate the cofactors, make sure you put in the signs. Okay. And then for the determinant of A is going to be equal, if I expand along the first row, A11, C11, A12, C12, plus A1n, C1n. Okay, so this is an expansion along the first row. Okay. All right, now what we showed, or what we actually stated, was that it doesn't matter whether you expand along the first row or the fifth row or the 10th row, or it doesn't matter if you expand down the fifth column or the seventh column or the eighth column. You just expand along one of the columns or one of the rows, and the formula is the same for any expansion. So the theorem is that the determinant of A, I'll state it twice, one for the row and one for the column. So here's the row expansion, AI1, so this is the ith row, CI1 plus AIN, CIN. So this is a row expansion here. So you're expanding along the ith row, and then you get these, you get the entries times the cofactors, okay? And then if you want to expand along the columns, you fix the jth column, and so I get A1J, C1J, A2J, C2J, plus ANJ, CNJ. And this is a column expansion. Okay? All right, so let's go back to this example. So this is an example from last time. And see what we get. Okay, so if I take the determinant of this matrix here, 4, 3, 0, and 6, 5, 2, and 9, 7, 3. Okay, so sometimes we write the determinant, we use absolute value signs. So 4, 3, 0, 6, 5, 2, 9, 7, 3. Okay. Now, when you calculate the determinant using this cofactor method, you can expand along any row or any column. You could take your choice. So, you know, it's more wise to actually pick a row or column which has more zeros, because then there are less computations you have to do. So let's expand along the first row. So I get 4 times the cofactor, let's just write it out, C11, plus 3 times the cofactor, C12, plus 0 times the cofactor, C13. Okay, that's by the formula. Okay. So now we just have to calculate all the cofactors. Okay, so we don't have to worry about this one because it's a 0. So this is 4. Now I have -1 to the second power. And when I cross out this first thing, I get 5, 2, 7, 3. And then 3 times -1 to the 1 plus 2, that's 3. And then I have to take the determinant when I cross out this one and that one. So that's 6, 2, 9, 3. Okay? Is everyone all right with that? Okay. And then you just take the determinant of the 2 by 2 matrices. So notice that when you take cofactors, you reduce the size of your determinants by 1, and then you just iterate the process. So what do I get? I get 4, okay, -1 squared is just 1. So I get 15 minus 14, and then plus 3 times -1, and the determinant is going to be 18 minus 18. Here, 80 minus BC, right? And so the answer is going to be, yeah, we did this last time. Okay, any questions on this? Okay, good. All right, we actually did another example last time too. All right, so now we're almost caught up. So here's the theorem that we showed. So let A be an upper triangular or lower triangular matrix Okay. So then the determinant of A, in this case, is just the product of the entries along the diagonal. A11, A22, and. Okay. All right, so that's a recap of things that we did in the Monday night session. Are there any questions on this? All right, so now what we'll do is we will start to actually move into using Gaussian elimination to compute determinants. So this next part is called properties of determinants. Okay. All right, so now I want to kind of go through the Gaussian elimination procedure and say what happens at each stage of Gaussian elimination. So let n be an m by n matrix. Okay. So what are the things that we can do? Well, when we use Gaussian elimination, so for Gaussian elimination, we can like interchange rows. Okay, so we have to know what happens to the matrix determinant when we interchange rows. Okay. Now, the second thing we can do is we can add a multiple of one row to another and replace a row. Okay, so we can add a multiple of one row to another. And then replace a row. Okay? And the third thing is we can multiply a row by non-zero scale. Okay? So any of these three operations, they don't change the system of equations. They don't change the solution set. Okay. All right. So let me go through what happens. Okay. So let me only change colors here. I don't know. We'll just go with Bulldog Red. How about that? Okay. All right. So what happens with number one here? Okay. So let's say B is a matrix obtained by interchanging rows of A. Let me say two rows of A. Sorry about that. Not just arbitrary numbers. Okay, so two rows of our matrix A. Okay. So then the determinant is equal to -1 times the determinant of A. Okay, so when you interchange two rows, then the determinant changes by sign in terms of -1. Okay. So how about 2? Well, 2, it turns out the determinant doesn't change at all. So the determinant of B actually equals the determinant of A. Okay. And 3, if lambda is the scalar, so let's make lambda the scalar here. That changes back here. So let's make lambda the scalar over here and change this back to red. Okay, so then it turns out the determinant of B is going to be equal to lambda times the determinant of A. Okay, so if you multiply by non-zero scalar on a certain row, then that scalar gets multiplied outside. Okay, so you have to take that into account. Now, for practical purposes, when we use Gaussian elimination, we only use properties 1 and 2 to get down to U, right? So suppose that So we really don't have to worry so much about property 3, but I just wanted to mention it. Okay, so suppose U is the matrix in echelon form obtained from A. Okay. So then, well, if I don't have any row exchanges, then I'm only using property 2. So I'm not going to change the determinant at all. Okay. So I'm not changing the determinant at all when I'm going by just multiplying one row, adding it to another, and just replacing. So the only time that I'm going to be actually changing the determinant is if I switch rows. So the formula is the following. It's -1 to the R times the product of the pivots in U. This is if A is invertible. I'm running out of space here. Okay, so if A is invertible, then we know that the product of the pivots in U is not equal to 0, right? And then it's 0 if A is not invertible. Okay, because one of the pivots will have to be 0. And R is the number of row exchanges. Okay, so you just have to keep track of the number of row exchanges. You take the product of the entries along the diagonal of U, and then you're good to go. Okay, so any questions on this? All right, so we're going to do 2 examples. All right, so let's do some examples where we compute the determinant using Gaussian elimination. Okay, so here's the first example. So I'll just write it out in terms of this notation. Okay, so 1, 3, 0, 2, -2, -5, 7, 4, 3, 5, 2, 1, and 1, -1, 2, -3. Okay. Now, as you can see, I mean, this doesn't have any like entries which are, well, it has one entry which is 0, but you know, it would be actually a pretty cumbersome task to compute the determinant using cofactors, right? Because I have to take this 4x4 matrix, and then I get cofactors, and I have to do a 3x3, and then when I have a 3x3, I have to go to a 2x2, and then I can compute the determinant. But if we use Gaussian elimination, we can actually shortcut the process quite a bit. It's a lot faster. Okay, so let's kind of row reduce. So I'm going to multiply the first one by 2 here and see what we get. So it's not going to change the determinant, right? 1, 3, 0, 2. And then we have a 0 here. And then what else do we have? 6,
1.
1. Okay, good. Next one is a 7.
7.
And the next one is
8.
8. Okay. And then we're going to multiply by -3 here. So what we get? We get a 0. And then what do we get?
-4.
-4. Okay, next one.
2.
2. Is that right? And next one? -5, right?
Yeah.
Okay. And then finally, I'm going to multiply this one by minus 1. Okay, we got a 0 here. And then minus 3 minus 1, that's minus 4, right? And then we get a 2. And then we get a minus 3 plus 2, or minus 3 minus 2 is minus 5. Okay, everybody all right with that so far? Okay, let's keep on going. All right, so let's eliminate the next one. Okay, so I'm just going to use the minus 4 as a multiplier. So the determinant doesn't change because we're not doing row exchange. 0, 0. Okay, what do we get? Okay, so we get 28 plus 2, that's 30, right? And then we get 32 minus 5. I get 27. All right, and the same thing holds with this one over here. Okay. All right, so last thing we have to do is we just want to eliminate the last one. So it's 1, 3, 0, 2, 0, 1, 7, 8. Okay. 0, 0, 30, 27. And what's the last row equal to?
0.
Row of zeros.
Row of zeros. Thank you. All right. So in the process, I use Gaussian elimination, using row sort of row reduction at every single stage. Okay. So what is the determinant here?
0.
Good. So the determinant is 0. Okay, so it's just a product. It's an upper triangular matrix. The product of the entries along the diagonal, which is 0. Okay, any questions on this? All right, let's try another one. So, actually, how did I label this? Oh, I labeled it that way. Okay, so let me just do that then. Okay, so let me redo this. So this example 2. All right. So I'll give you this determinant. So it's 1 minus 1 minus 3, 0, 0, 1, 5, 4, minus 1, 2, 8, 5, and 3 minus 1 minus 2, 3. Okay. All right, good. Okay, so let's see what happens here. Okay, so let's take so the first one we don't have to worry about. That's already a 0. So let's just multiply by 1 and add it to the third row and put the result in the third row. Okay, so the second row is okay. So what do we get? We get 0. Then what's the next one after that?
1,
1. Okay, next one.
5,
5, right?
and 5.
1, 5, 5. And then the next one we're going to do is a minus 3, and we're going to add it to the fourth row, and put it in the fourth row. Okay, so let's do that. That's a 0. And then we have a 3 plus 1, that's a 2. And then minus 2 plus 9, it's 7. And the last one should be 3. Okay. Everybody okay with that so far? All right, keep on going. But notice that, even though this is, 4 by 4, it's still not too bad. Okay. All right, so let's get this. This is 0, 1, 5, 4, 0, 0, 0, and then what do I get? 1. Okay. And then I'm going to multiply this next one by minus 2. Okay, so I get 0, 0. Okay, it's minus 10, 3, it's minus 3. And the last one is minus 8 plus 3, that's going to be a minus 5. Okay. All right, so we're down to the stage. Okay. What do we need to do next?
Row exchange.
Okay, what rows do we have to exchange?
3 and 4.
Okay, so what's it going to do to determine if we row exchange?
It's gonna make it a negative,
Right.
or we have to add a negative
So
or
we
multiply a -1 to it.
right. So this is minus 1, minus 3, 0, 0, 1, 5, 4, 0, 0, minus 3, minus 5, and 0, 0, 0, 1. Okay, is that clear? We have to put the, let me just circle it. I'll circle it in red again here. So this is due to row exchange. All right. Okay, so now everything's good. And now what's the determinant going to be?
3.
3. Okay, so it's minus 1 times the product of the entries along the diagonal is minus 3, and the answer is negative. Okay, any questions on this so far? All right, good. All right, so now let me state the theorem. So the theorem actually follows just from this formula up here. So if A is not invertible, then the product of the entries in U has to be 0, right, along the diagonal. So that means the determinant is actually equal to 0. And then conversely, if the product of the entries is not equal to 0, the pivots is not equal to 0, then all the pivots cannot be 0. So then we could actually find an inverse. It has full rank. So the theorem is that A is invertible if and only if the determinant of A is not equal to 0. Okay, so this follows by our analysis using Gaussian elimination. Okay, any questions so far?
Yeah, I have a question real quick.
Yeah, go ahead.
Why is that matrix equal to -1 times -3?
Because we did a, well, what do you mean? Why is the which matrix?
So this last problem we just did, where basically I understand where the -1 comes from because you have to do that for the row exchange, but why -3?
Oh, because I took the determinant of this upper triangular matrix, and it's the product of the entries along the diagonal. The thing in the absolute value means take the determinant. And whenever you have an upper triangular matrix, the determinant of an upper triangular matrix is the product of the entries along the diagonal. So it's 1 times 1 times -3 times 1.
Oh, okay. Okay, that makes sense.
Okay, so we're using this theorem right here. See, once you have it in upper triangular, lower triangular form, it's easy to take the determinant. You just take the product of the entries along the diagonal. Okay, so that's the whole idea, is that we want to get it into an upper triangular or lower triangular form. We know how to do that using Gaussian elimination. So we just have to keep track of what happens at every step when we apply Gaussian elimination. Is that clear?
Yes, that makes sense.
Okay, good. All right. Now, what I want to do is to show you a trick. So So this is a trick for computing 3x3 determinants. Okay, so the first warning is this does not work for n bigger than 4. So warning. If you want to call it a caveat, you can. So this does not work for 4x4, 5x5, etc. So any matrices which are higher dimensional, this does not. All right. So here's the idea. So if I want to take a determinant of a 3x3 matrix, maybe people have seen this before. If they've taken things like cross products. Okay, so these are the entries of a 3x3 matrix. All right, so the idea is the following. I don't know if you guys, things are, retro things are kind of in now. So has anyone played the game like Asteroids before? Yes? Oh, good. All right. So this will make it easier to explain. All right, so what's the idea in terms of asteroids? You have the spaceship, and the spaceship kind of goes along the screen, but it reappears on the other side, all right? So like the spaceship can kind of come down here, all right? So let me just write the entries down. So these entries are A11, A22, A33. Okay, so I'll just put them with the positive sign. Now, if your spaceship is going down this way, it kind of comes off the screen and it picks up this one over here. So I'll add to it, A12, A23, plus A31. Okay? And then finally, let's say you're over in this part over here, and then it's going to reappear on this side over here. So I got to add A13 plus A21 plus A32. Okay, this is times over here. Okay. Maybe I'll just erase that, just so it's not confusing. Okay, so those are the positive entries, right? Okay, so now what I'll do is I'll use blue here, and then we'll do the negative entries. Okay. All right, so for the negative entries, we're going to go down this way. Okay, so I have negative A13, A22, A31. All right, and then similarly, we go down here, and then we have to re-enter over here. So it's negative A23, A32, A11. Okay, and then one more negative here. And we have this one here, and we have these two. A33, A12, A21. Okay, so there's 6 terms. There are three terms where you go down from sort of left to right. And then there are 3 terms where you go down from right to left. Make sure we put in the signs correctly. And this is the formula for the determinant. Okay, I'll leave it as an exercise for you to verify that. So this is the formula for 3x3 determinant. Okay, so you don't have to take cofactors, you can just go along diagonals in order to calculate the 3x3. Okay, any questions on this? All right, good. All All right, so now I want to give you some more properties about determinants. Is the section name? Yeah, okay. So I'll just say more properties here. Okay, so these are more properties of determinants. All right, so we already talked about how to compute determinants using Gaussian elimination and the fact that if A is invertible, then that happens if and only if the determinant is not equal to 0. So let me state a few more theorems. So this can be proved using the definition of the determinant. So whenever I take the determinant, it's the same thing as taking the determinant of A transpose. Okay. That's not so hard to sort of, it's pretty easy to believe this because we could either do row or column expansions to compute the determinant. So by taking the rows of A, they turn into the columns of A transpose. You can kind of believe that this is true. Okay, so the second theorem, which is the deeper theorem, takes some more work to prove, is that if you take the determinant of the product of two matrices, so here A and B are n by n matrices. Okay, so if I take the product of the A and B, then that's the product of the determinants. Okay, so with respect to matrix multiplication, the determinant is multiplicative. Okay, so let's, okay, we have time to do a quick example. So let B be equal to 1, 0, 1, 1, 1, 2, 1, 2, 1. Okay, so I want to compute the determinant of B to the fifth. Okay, so there are a couple ways I can do this. So one way is if I take B and I multiply it to itself 5 times. All right, now that's going to be kind of a pain, right? But what do we know about the determinant of B to the fifth? Well, determinant of B to the fifth is equal to the determinant of B times B times B times B times B. Okay? But we also know by the theorem above, that's the determinant of B times the determinant of B times the determinant of B 5 times. Okay? So in particular, it's just the determinant of B raised to the fifth power. Okay? So as long as we compute the determinant of B, we can just raise it to the fifth power. And that's easy, that's just a number. Okay? All right, so let's compute the determinant of B. And so it's 1, 0, 1, 1, 1, 2, 1, 2, 1. And now I'm going to use my little asteroids formula. Okay, so I'm going to go down the diagonals. Okay, so let's go down. I don't know. All right, I'll just switch the colors really quick here. Okay, so I need to go down this diagonal, and this diagonal first. Okay, so let me just write the numbers now. So it's 1. Okay, then I get plus 0, right? Because 0 times 2 plus 1. And then what's the other one? 1 times 2 is 2. Okay, good. All right, now we'll go down the blue way. Oh, sorry. Okay, so we're going to go down this way. Okay, so we have negative signs, right? So negative 1. And then we have 2 times 2 times 1 is negative 4. And then we have 1 times 0 times 0 is minus 0. So let me try to switch pens again. And what is the answer here? It's going to be 2, right? Actually, it's 3, right? 1, 2, 3. And let's see, minus 5, right? That's minus 2. Okay, so the determinant is minus 2. And so the determinant of b to the 5th, which is equal to the determinant of b raised to the 5th power, is minus 2 to the 5th, which is minus 1. Anyone?
32, 16?
32. Okay. Okay, any questions on this? Yeah. Where did I get this 4? So I got it from 2 to 1. Right? I need to go down to it. Okay. I think it's correct. 1, 0, 1, yeah, because this looks correct. And then 1. Right. Right. Okay, other questions? Okay, so we will look forward to seeing you on Friday.